Now we're going to do a question that is about concavity and inflection points. So here is the function. Um, so kind of like last time, it's just a polynomial, very nice. And so what is the rule that we're going to use to figure these things out? So kind of similar to what we did last time, on which intervals is f concave down? So those are going to be the intervals where the second derivative is negative, okay? And on which intervals is f concave up? Those are going to be the intervals on which the second derivative is positive. Okay, so notice how similar this is to what we did in the previous problem. It basically amounts to just telling where a function is positive and where it's negative, right? So how do we do that? Well, first let's figure out what the second derivative is. Okay, so the first derivative of this thing is the 5 comes down, and you get x plus 1 to the fourth. And then you kind of want to spit something out by the chain rule, right? But it's just 1. The derivative of the inside stuff is 1, right? So that's all there is, really. And minus 5. And we're going to be looking at the second derivative. So the second derivative is, you're going to get 20 times x plus 1 cubed. And again, that's all there is because the derivative of the inside stuff here is just 1. And this constant goes to 0. And so this is all. So our strategy for finding where this function is positive and where it's negative is exactly the same as before. We're going to break the line up into regions that are separated by the roots of f double prime. So as you can probably see, it looks like this thing has 3 roots, but it actually just has a root at -1. Okay, so, and I hope you agree with me. So -1 is a solution here, and then there are some imaginary solutions. Okay. Alright. So I've already solved this. I hope it's obvious to everybody why -1 is the answer. And so I'll just go ahead and break up the line into the regions. So now there are only 2 regions. So here's one and here's one. So let me make the chart. I'm going to go from -infinity to -1, and from -1 to infinity. Okay. And here I'm going to write f double prime, and just like last time, I'm going to be saying whether this is positive or negative. And I'm going to write f here. And so in the f column, I'm going to write what the sign of f double prime says about what f looks like. So the rule here is simple. If this is a plus, then f is concave up. If this is a minus, then f is concave down. And we can find whether it should be plus or minus just by testing a point in the interval. So for this first part, let's pick -2. Okay, so we're using -2 as our test point. So what happens when we plug -2 in here? Remember, negatives raised to an odd power are still negative, right? So this is going to be 20 times -1 cubed is going to be negative. So this is negative. That means f is concave down. And we have one, I did that last time, didn't I? I have one more interval left to check. So a nice test point there is just 2. So what happens if I plug 2 in here? I get just 20 times 3 cubed, right? I don't know what that is, and I don't care because I can tell that it's positive. And positive means that f is concave up. Alright, and so now I'm done with A and B. This question is much easier than the other one, isn't it? Maybe just because we had some practice. So here I'm going to write the answers to these questions. So on which intervals is f concave down? So the interval, there's only one, on which f is concave down is the interval from -infinity to -1. And on which intervals is f concave up? Well, there's only one, and it's the interval from -1 to infinity. Okay, great. So the only thing left is C. So C is about inflection points. And maybe I should just say something about what is concave up, what is concave down, what is an inflection point. So this is what a region which is concave up looks like, right? Where this black curve is supposed to be the graph of f. And if it makes you feel more comfortable, you could draw some axes here. So things are going on with respect to some axes. And so this is going to be a region on which f is concave up. And this is going to be a region on which f is concave down. And this part C is asking about an inflection point. So what is an inflection point? An inflection point is a point at which f changes from concave up to concave down, or vice versa. So if it changes from concave down to concave up like this, then that would also be an inflection point. Alright, and so how do you detect those things? Well, inflection points are points where the second derivative changes sign. So maybe I should write that down. Okay. So f has an inflection point at C. So what does C mean? So C is like this number on the line. So f has an inflection point at C if f double prime changes sign at C. So this is a definition. So it's really if and only if. Okay, and maybe we should just say a couple words about why that should be true. So the idea here is that if you look to the left of the red point, then for some of this, if you look at the concave up region, sometimes the tangent line is negative and sometimes the tangent line is positive. But what you should notice about this entire cup up or concave up part is that f prime is increasing, right? It's getting bigger and bigger and bigger. So compare that to what's happening over here on the concave down part. Okay, so on the concave down part, sometimes the tangent is positive and sometimes the tangent is negative. But what's happening is that for this entire part, f prime is decreasing. Alright? And so f double prime is the derivative of f prime, just like f prime is the derivative of f. So this increasing and decreasing rule that we talked about in the previous problem applies here. And so f prime is increasing exactly where f double prime is positive, and f prime is decreasing exactly where f double prime is negative, which is why this table gives us the correct answer. Okay, and so what does it mean for f to change from concave up to concave down? Well, by this argument, it just means that f prime changes from increasing to decreasing, or vice versa. And what that means in terms of the second derivative is that the second derivative changes sign from positive to negative, or vice versa. And you probably just want to strangle me, right? Because the answer is totally obvious. There's only one place where this function has an inflection point, because there's only one place where the second derivative changes sign. And you can see that it's right here at x equals -1. F double prime changes sign from positive to negative. So this function has only one inflection point, and the x value where it occurs is x equals -1. And that's the end of the question.